Okay, so in this video, we're going to look at two more properties of Fourier transforms, and those are the convolution and multiplication properties. Okay. And these properties are going to be very important for us. We're going to be using them throughout the class. And we've actually already seen one of them in the LTI system box diagram. Okay, and that is the convolution formula, which I'll write down here, and it should look familiar. Okay, but that was in the context of an LTI system with an input and an impulse response. Here, we're just going to look at two functions, just any functions, f and g. Okay, and we saw, if this was my input and say this was the frequency response, right? Say x of t convolved with h of t in an LTI system, we saw the Fourier transform was going to be x of omega times h of omega. Okay, we saw that in the context of LTI system outputs, but it turns out it's true in general for functions. So any f of t convolved with g of t, the Fourier transform of that convolution is going to be f of omega times g of omega. Okay, so this can be really useful when you're solving problems because often this convolution operation is at the very least time consuming and tedious to perform. And sometimes Fourier transforms are easy to perform. And then, of course, the operation of multiplication is often easy as well. So this can be a very useful operation to keep in mind, or a very useful property to keep in mind. Okay, so let's see how it's proved. Okay, so we're going to start with the left side. We're going to take the Fourier transform of f of t convolved with g of t. And we have our e to the negative j omega t dt. Okay, now let's plug in for what the convolution is. Remember, what is the convolution? Well, it's the integral. Okay, and we'll talk more about this in a later video in more depth, but at least the definition of the convolution is it's an integral, okay, of f of tau g of t minus tau d tau. Okay, so this is the convolution of f and g. And one thing to notice is that these arguments here always add up to t. Okay, so tau plus t minus tau is t. Okay, so this entire thing is an integral d tau. It gives us a function of t, and that function of t is the convolution of f and g. Okay, but we'll talk more about this in a future video. For now, we just need the definition. And then we have e to the negative j omega t dt. Okay, so now I'm going to switch these integrals. Okay, and what do I get then? Well, now this outer integral is going to be the d tau integral. So I can pull this f of tau outside. And then the inner integral is going to be the integral of g of t minus tau, e to the negative j omega t dt, and then d tau is outside. Now, what does this inner integral look like? Well, it looks like a Fourier transform. A Fourier transform of what? Well, of this function, right? This is just the Fourier transform of g of t minus tau. This is the Fourier transform of g of t minus tau. Okay, and we saw that Fourier transform property. Okay, what is the Fourier transform of a time-shifted function? Well, it's our original Fourier transform, g of omega, times a phase shift, and that phase shift is e to the negative j omega tau. Okay. All right, so we can plug that in. So we're going to get f of tau, and then g of omega, e to the negative j omega tau d tau. I'm going to pull the g of omega out because it doesn't depend on tau. We have f of tau e to the negative j omega tau d tau left over. And now what does this look like? Well, that right there is just the Fourier transform of f, right? Don't be fooled by the integration variable tau. Whatever we call that integration variable doesn't really matter. You could put t's in there if you want at this point. I just needed tau because I already was using t. That's just the Fourier transform. That's it. It's the Fourier transform of f. And so what we're left with, I'll just write it in alphabetical order, is f of omega times g of omega, which is just what we want. Okay, so now we can see that if you ever have a convolution and you want to look at its Fourier transform, you can take the Fourier transforms of each function, f and g, and then multiply them, and you get the Fourier transform of the convolution. Okay, so that is the convolution property. All right, and there's one more property that is sort of the opposite to this one in some sense. We're going to see exactly what sense actually in the next video when we talk about duality. Okay, but what is the multiplication property? Well, we can see that we have convolution in time and multiplication in frequency. What happens when we have multiplication in time? Okay, what happens when we have multiplication in time? What's the Fourier transform? Well, wouldn't it be nice if it's convolution and frequency, right? If we have sort of this flip-flop, convolution in time is multiplication and frequency, multiplication in time is convolution and frequency, and it almost is. Okay, we just have this extra 1 over 2 pi factor. 1 over 2 pi f of omega convolved with g of omega. So now we're convolving in the frequency domain here. Okay, so you can see how these two properties are sort of paired up with each other. All right, so let's prove this. It's going to be pretty similar. I'm actually going to start with the convolution side. I'm going to take the inverse Fourier transform of the 1 over 2 pi f of omega convolved with g of omega. And I want to end up with f of t times g of t. Okay, so what do I get? Well, I have my 1 over 2 pi, that constant right there. Okay, times, now I'm going to get actually another 1 over 2 pi from this inverse Fourier transform formula. Right, this is our inverse Fourier transform formula of f of omega convolved with g of omega. Okay, so we have that term, and now we're going to proceed actually in a pretty similar way. We're going to plug in for what that convolution is. Right, so what is this convolution? Well, again, it's an integral. And now I need a new variable. I'm just going to use v. We're going to have f of v, g of omega minus v, dv, and then e to the j omega t d omega. Okay, so you can see again that these arguments always add up to the variable that our resulting function will have, in this case omega. So v plus omega minus v is omega, and that is the variable we were using in our convolution. Same thing up here, tau plus t minus tau is t, and that was the variable we were using in our convolution. Okay, so that's kind of the hallmark of convolution. Those arguments add up to the variable we started with. Okay, so this is what we have. Now I'm going to switch the integrals again, just like we did above. Okay, so what do I get? Well, I'm going to have a 1 over 2 pi. Now I'm going to have an integral. Now, instead of being the d omega integral, this is now the dv integral. And so I can bring this f of v outside. Okay, now I'm going to bring one of those 1 over 2 pi's inside. You can see I'm trying to kind of write this as an inverse Fourier transform formula. Now I have g of omega minus v. Okay, that's left over. I have e to the j omega t d omega dv. Okay. Now what do we have here? Similar to above. Okay, that is the inverse Fourier transform of what? Well, of this function, right? A frequency shifted version of our g. Okay, so this is the inverse Fourier transform of g of omega minus v. And if you plug that into the inverse Fourier transform formula, this is exactly what you would get. Okay, and we saw that property as well. Okay, we just get our original g of t, but again, multiplied by this phase shift, j v t. Okay, so that is that property we've seen before, the inverse Fourier transform of a frequency shifted version of, in this case, g of omega. So now I'm going to plug that in. And I get 1 over 2 pi, the integral f of v. Now I have g of t, e to the j v t dv. All right, I just plugged in what we just found. Now I can take the g of t out because it doesn't depend on v, and I'm left with 1 over 2 pi times the integral of f of v e to the jvt dv. And what is this? This is exactly our inverse Fourier transform formula. And that gives us f of t. It's the inverse Fourier transform of f of v. That's all that is. Right, that's all that is. I'm using the variable v here instead of omega, but again, just like we saw above, of course, whatever we call that integration variable makes no difference. And so what am I left with? Just f of t times g of t, which is just what we wanted. Okay, so these two properties are really useful not only in the context of LTI systems, as we've already seen, okay, but we're going to be using them for other reasons as well and other applications. Okay, so if you ever have a convolution in time and you want to take the Fourier transform, you get the product of the Fourier transforms of those two functions. And if you have multiplication in time, then you do get the convolution of their Fourier transforms, but you have to remember this 1/2 pi factor as well. Okay, so those are two useful properties, and we'll be using them in videos to come. And that's all I had for this video. I'll see you in the next one.